I guess I'm listed organizer, so I cannot thank the organizers, but I should thank the real organizers, people at IPAM. I want to you guys to think my talk is like what happened yesterday, a continuation of the poster session. So here are my posters. I will do a 15 minutes extended advertisement for those two posters. So I think my collaborators are in the audience, so feel confident. So what I want to tell you is more or less kind of a story to convince you. Actually, now I think it's a mathematical conjecture. So suppose B is an annual model. So you only need to know one, because that's the only one I will mention most of the time. And this is the famous toric code. So it's a rank 4. There's the vacuum. There are two bosons. There's a fermion. Nothing anionic at all. But the mutual statistic tells them they are not quite boson fermions. So that's the only thing which is kind of new. And mathematically, this is called a unitary modular tensor category. And if you were here for Colin's talk, I assume you guys are all expert now. It's just a way to draw pictures. So the conjecture, which was inspired by this paper, and then continued here in a much sophisticated way, which I couldn't understand. I will tell you the story. So, and then there's another, I will mention another aspect. So the conjecture is that if you take So I will explain basically this conjecture and the consequences. And even if this is not correct, I want to convince you this is very interesting. So, so this side, the left, will be the moduli space of all topological theories which realize this topological order. So by topological order, I mean an annual model. And this side, this is I will spend quite some time explaining to you because this is very high categorical thing. B stands for classifying space. And PIC stands for Picard. And this is your annual model. And this two line means you raise the categorical number twice. And this is the categorical 2 group, which is a 3 groupoid. And you build this classifying space. And this is the topological space. And I will explain how to build this, everything. And the thing which this side, there are 3 ways to think about it. One is you think about Hamiltonians. And this basically lattice models realize this annual model. It's not clear what I mean by realize, but let's not go there yet. And the second way to think about it, you can think about the Lagrangians with parameters. And the low energy effective theory of this will be this TQFT. Now this is mathematical, at least I don't know how to do it, but there is a mathematical way, which is you can consider a gapped states which realize this topological order. And I claim this is mathematics. I'm not good enough to tell you the story, but I can tell you where to find it. So there's a recent series of papers by Yoshiko Okada. She's a professor of the University of Tokyo. I'm moving to Kyoto in a month. So she defined what is a gapped state and what do you mean by realize this annual model? At least for a billion annual, double of a billion groups. That depends on a very difficult theorem where they came up in the last talk. with a Haack duality. And it's not true in this context, but she defined one of the deepest things, which is called approximate Haack duality. And I believe this is the mathematical for you to prove this conjecture. This is a hardcore operator algebra, algebraic quantum field theory. This is the mathematical conjecture because I give you two definitions here. And I want to convince you, even if I'm wrong, it's still very interesting. Okay. So there are two origins of this conjecture. One is the paper of me and Matt. And we try to study this problem using the Hamiltonians. And the whole purpose is to come up with a framework to understand the Hastings-Haah code. So I will see a little bit. And the second origin is Po-shen, my collaborator, and Kapustin and Ran Thorgren. They have a slightly different take, but I think this is the worst I believe. They did using a slightly different topic, but basically using generalization of a Berry phase, Thales pump, which I will mention a little bit, and it came up something related. And but this is the version I want to convince you, which is the correct one. By the way, stop me anytime. So that's basically what I want to talk about. So I will start with the motivation. And then I will tell you this side. And then I will explain this effective theory approach. So basically, that's my plan. So let me start with the motivation. I already told you that we started in this paper trying to understand the Hastings-Haah code. And this conference is about topology, error correction, and quantum gravity. I don't have anything to say about quantum gravity, but I will say a little bit about topology. So I don't know who originated this idea, but many people share. And of course, if you think about topological quantum computation, it started with Alexei Kitaev and Michael Friedman. So the point is that if you think about local errors, and what can be resistant to local errors, topology is an obvious answer, one answer, because think about local error, that's just like perturbation. And topology exactly tells you I want something which is not amenable to local perturbation. So that's kind of the key point of topological quantum computation. And you can make this into mathematics by doing the following. So if you take any point inside this moduli space, let's take the first point of view. I realize this by a Hamiltonian. And then you will have a ground state of your Hamiltonian inside some local Hilbert space. It's a mathematical theorem. This is an error correction code. And it's my former student Shao Cui proved for dream fields for quantum double of Kitaev model. It's another former student of mine who proved for the Zhenghan Wang model. So this is a mathematical theory, the error correction code. And more than that, we prove something stronger, which is they also satisfies the conditions given by Matt and his collaborators, which are they are stable with respect to local small perturbation. And that means we need to prove two conditions. They call TQ1 and TQ02. And this is basically saying this ground state is error correction code. And this one basically says your ground state has to be homogeneous. That is automatically the translation environment. And for the topologies, this has a very easy explanation. This is something called a disk axiom in TQFT. And this is called the annulus axiom. So in the TKFT language, if you put, I'm only talking about 2 plus 1 dimension. So that's my space. If you take your 2-dimensional space, and the disk axiom says, if you put your theory onto it, and as long as no topology, which means the piece of space is a disk topologically, you cannot get any state, just trivial one-dimensional. And that's basically the first condition of error correction. Basic error correction code means that this guy behaves as a one-dimensional space. So what is special one-dimensional space? If you take any linear map from one dimension to one dimension, you either get identity or you get 0. That's the only 2 things you can get. You get identity after scalar, that means no error. You get 0, it means the error is perpendicular. And by quantum mechanics, you can measure it and fix it. So that's the first one. And the second axiom says you expand this by a small annulus, they are consistent. So that's the 2 conditions. Those got discovered, but I don't believe they think this way. So that's the first connection to topology and error correction. And then the second one is my real motivation for this whole thing is that instead of study a point here, I should study a loop. And this basically underlying Hastings-Haah code. That's basically what it is. So I will see a little bit more. And then Dave told you about dynamical code, and I believe that's roughly a line in here. Okay. So that's my first sell to you. This is interesting if you study error correction code. Of course, error correction code is not topology. Error correction code has all this distance, all those things. That's actually geometry. So you have to go a little bit beyond. But it's basically a topological realization of this. And then how do you realize? That's give you the geometric properties of the code. So that's the first motivation. Yeah? Sorry. Yeah, sorry.
I'm sorry, could you please repeat your definition of error correction code in this
So one of the mathematical way to define error correction, actually already seen in the talk before, but I think they should put a face there. So any code roughly is a subspace of another one. And error correction just means you take your space, you embed it into this bigger space. You take any local operator, you project, and this composition should be lambda times identity V. So it means that this local error can only do 2 things, nothing or perpendicular. So that's my understanding of error correction code. So this is the first motivation I'm interested in this space. And the second reason I'm interested is a very fashionable topic right now, which is higher symmetry. So as a mathematician or topology, you ask me, what is symmetry? And the most general way to think about symmetry for me is, and this is what it is. So you take anything ambient, and you choose a subspace, like a knot. And why I think this is a symmetry? Well, this is kind of the beginning of symmetry in history. This is Galois theory. So what this N tells you is, instead of thinking everything to this one, you should think about relative to this one. Think for all those move here, but take this one back either as a set or literally. And that's basically what this symmetry would be. And that's underlying the so-called defect and the symmetry. An example would be take a disk. Nothing there. Every homomorphic topological identity. But if you put an endpoint there, and now you have a very beautiful group, the braid group. So I chose these two letters actually for people who know the subject. This is due to Wang Jun. This is the whole subject started. This is the subfactor theory. And another way to see it algebraically is why I would consider this as a symmetry, because you are looking for automorphism of M so that N equals Mg, the fixed set. And that's actually normally all the symmetry gives you. And that's why John started the subject, which is started with this one, semi-direct product of group action on here, and then all the index generalization is just the index of a group. And that's also Galois theory. So for that reason, if you think about symmetry as a topologist, no way you can miss what I want to go. This is a class-infinite space. And this is the generalization of a group. And you have to study topological gauge theory, study bundles. So basically, I want to convince you to study principal bundles instead of a finite group. You want to do this categorical two group, which is a three group point. So, and Po-shen is the world expert on those things. So that's what I'm going to tell you, which is the effective field theory. And the way to think, this is not really outrageous, is the following. So if you take any topological order, which by me is a linear model, and then there is a whole blue book by Triep says you can construct a TQFT in the sense of Artia. It's a functor from space-time to the vector spaces. But if you think a little bit more, you realize this TQFT always comes with a symmetry. So the symmetry is, so this is always enriched by Picard B. And this is a finite group. As I said, I will only do one example, so let's do toric code. I forgot I use epsilon or psi. I use them randomly. So the Picard group of toric code is Z2. And what are the two elements? There are two ways to think about it. One is to think about as linear permutations. So there's the identity, which you do nothing. All mathematicians, we include identity for all kinds of purposes. And then there's the incredible deep one, which is you can permute those two. Okay. That's the so-called EM symmetry. Okay. And of course, the letter is chosen to say this is a generalization of the real electromagnetical duality, which is true. And then this is a fermion, which is a composite. So now you see that for toric code, actually, there is a Z2 symmetry there. As I said, the fashionable thing to do is to think about higher symmetry, which means instead of thinking about group, you should think about categorical group, which is higher, which is much more subtle. That means I want to promote this guy to a categorical two group. And I will give you the definition a little bit later. It's not always true. You can promote this from Picard to a categorical two group. I have worked out a whole theory with a bunch of collaborators many years ago. There's an obstruction in H alpha 3, there's an obstruction in H alpha 4, but you can do this sometimes. Basically, for those who know the theory, is just you take the G as this group, and then you try to lift it to a categorical two group. So therefore, every TQFT intrinsically has a symmetry in there already, and it would be terrible if we don't study it. And therefore, what I want to do is I assume always the obstructions are vanished, and I made some choices so I can lift it to a categorical two group symmetry for my TQFT.
In the case of the Fibonacci anyons,
That's trivial.
that would be contractible space.
Yeah. But the whole thing about categorical, that sometimes can be interesting higher thing. Fibonacci, there's nothing there. But if you take semia, you cannot permute them. but they're still interesting in fact, like a symmetry fractionalization, they come from higher categorical symmetry. It's a much subtle. This is like the only word I remember, something, I don't know how to pronounce it, this thing. What, to foot anomaly or something? That has to do with to lift into the first level. The obstruction to lift to the first level can be interpreted as to foot anomaly, and to lift to the second level is another obstruction. Sorry,
how do you pronounce this? Pictor or?
Oh, this is called Picard.
Sorry.
I will explain here.
Right, and this Picard for the toric code
Is it
Z2, and I should think of it as automorphism on the theory B itself.
So the technical term is tensor autoequivalence of your category. So it's a functor, preserve the tensor product, and preserve the braiding.
Okay.
Of course, up to natural transformation.
Do we understand the moduli space of 2D TQFTs?
I don't, but
we use manifold or something.
every category has a class-infinite space. So I'm not seeing anything. But the whole point I want to sell to you is basically to treat this as a suggestion. And you can study the cohomology, the homotopy, and then you can ask interesting questions like, what's the homotopy tells you about topological physics? What do it tell you about error correction code? And the same thing about homology. So even if it's just subjective, it's already pretty interesting. OK, so any other questions before I go to the real math to tell you this incredible complicated guy? OK, so I won't go back to this. I will, as I said, the paper I wrote with Dave and Matt is this point of view. I will talk about Lagrangian. And I won't touch on this one. This is a hard mathematical, way beyond my grade. So I will start with this one, the Picard. So this is a very old name. You take any field, complex number, real number, there's a Picard group. And this is a generalization to incredible abstraction. So the formal definition of Picard is the group of invertible module categories over B. Everything is up to the natural equivalence. So module category, you should consider this, just take like this is any ring or field. And a module just means a representation of this guy. And there's a categorical version of a module. The thing which you want to learn category is extremely simple. You just need to be absent-minded. When you look at the algebra formula, just forget about the formula. Just remember the picture. If you draw all the pictures, they all work out in other categories. And then they all work fine. And that's the same thing about module. You just write down the ring acting on a module. Just forget about the symbol. Just look at the picture. They all make sense. Invertible means if you have a module, and you can take another one, and you can tense them together. And here is already subtle. I'm using the braiding to turn any module category into a bi-module category. And then you can tensor over the bi. So this is a bi. And they are different. And then, of course, invertible means this is B as a module category. And there's a beautiful theorem due to UNO. I have to apologize if I wrote this wrong, but this one is correct. So I consider this one of the most beautiful theorem says defect is symmetry. It says Picard so the theorem is Picard is isomorphic to auto-braided tensor equivalent. Yeah. So this is all the functors, preserve all the structures, and you compose them up to isomorphism. And this is the invertible modules using this as multiplication. And they are the same. And I told you for toric, this is a Z2. So that's your two module here. And the identity, it goes to B. Or I think I should write 0, 1 probably. And the 1 goes to a module which is very interesting. I chose the sigma plasma to suggest to you that's actually the Majorana version of this. So these are two symmetry defect of dimension square root 2 and the basic version of Majorana, like Google is doing. So those are two symmetry defects and give you this. So that's the two modules. And now I want to tell you the promotion. So
Sorry.
Yeah.
That looks like it's homotopy equivalent to 2 points.
This is consider that using this multiplication and everything. It's a module category. So
But on the other side, you said it should be RP infinity, the classifying space of Z2. What you just erased at a classifying space on the
it's I don't know what it is. You know, if you do group, of course, it's RP infinity. But I'm going to do it as a categorical version.
Oh, is there a difference between capital M and script M that you just erased?
Yes. Okay. Yeah. Mike, I use M for module category, and I use the whatever you call this guy as the moduli space of topological theories. Realize this one.
Oh, so what's the symbol you just wrote there? What,
This is a module, so which means there are functors from B cross MB to this thing. And then let's give you a representation of a B into morphism of this module. So this is a
okay,
module.
so that had nothing to do
Has nothing to do with the classifying space.
And the sigma plus and sigma minus are just two objects in that category.
It's a two object in this category. And what you really want to, you can put them together. So this is a rank 6, and this is a module because this has a graded action. And this basically tells you, in this theory, toric code has a natural Z2 symmetry. And they have your anyons, and then they have two symmetry defect. And this one has no flux, and this one has a non-trivial flux, -1. And I can impress you more if you go one more step, make it dynamical, and that's the double of Ising. So that's a gauging process. There's some choices made. So that's the whole story about lifting.
Wait, what's BZ2 cross?
Oh, it's just a notation that if you want to gauge this Z2 symmetry, you start with a B, and then you do physics called minimal coupling. Goes to BG cross, and that's this one. And then you do so-called, whatever you call orbifolding, or no, this is orbifolding. And that's given the double Ising. So, and you can see they are really an avatar of the real Ising area. So that's basically, this at the level of a group. And now I want to do the fashionable thing, which I don't know will lead that to anywhere, but at least it's I learned the word is at least it's a new bottle for old wine. So it's a new way to think about symmetry. So the thing I want to say is that this Picard, the two line means this is a categorical 2 group, which means this is a 3 groupoid. This is a general phenomena. Categorical n group is always an n+1 category. It's a groupoid. which means every morphism is invertible. Okay. And a categorical zero group, so a categorical zero group, that should be a real group. And then you should think this as one object, and then every group element is a one morphism which is invertible. And that's how you think about a group as a categorical zero group. And as a three group, we know that for every group, you can construct this BG, this classifying space. And the easiest one to think about, of course, is Z goes to R, goes to cross S1. And then this is BZ, and this is E. And this is only defined up to homotopy. So the homotopy definition is you need to find a space which is contractible for group G, act freely, and then you take a quotient, that's your BG, and the fiber would be, of course, a group. And now I just want to mimic this construction. And the way to do it is using a very fancy construction called NURB. So basically, give me a category. I can use the composition of a morphism to build up a simplicial complex. And then I take a realization of this simplex complex. And that will give you this moduli space, this classifying space. And I will quickly outline for this particular case. So first, Picard is a three-groupoid. And I like this numerology because when somebody tells you, I have a three-groupoid or n-groupoid, and it's really mean it. Three-groupoid means there are three groups. So n-groupoid means there are n of them. And the generalization is for n equals 2, it's well known. It's called cross-module. For 3, it's called cross-complex. You just do this kind of sequence. Let's give you an n group. So now you can see I really should have three groups in here because that's what it is. So this classifying space. So first, this is a three category. Means I have 0, 1, 2, 3 as morphism. So as objects, I have only one, which is really should be B. And then I'm sure here I should have module categories, like I said there. And once you have this, mathematician automatically know the next one is functor, and then the next one is natural transformation. Okay. So that's the three categories you build. Everything is invertible. And now you want to construct a space out of this category. And this will be a CW complex. You start with one point. And then take your modules. Each of them become a loop. So that's my toric code. Okay? And now I need to add a 2 complex. And for those who are in Colleen's talk, that's exactly what she did. You want to add a 2 complex, you just draw your fusion rule. Okay? There's X, there's Y, there's Z. And there's a isomorphism between X tensor Y to Z. And then you attach this 2 cell, and the boundary would be plus, plus, minus. Go through this guy, object with the loop, one way, another way, and this one the opposite way. Okay. So that's given the 2 complex. And for 3 complex, maybe I will do here. So for 2 complex, it's just a fusion rule. For the 3 cells, so for 3 cells, it won't sit if you start a fusion. So that's your 3 cell. This is the tetrahedron. And there are 3 fusion here. And you attach to this 2 cell with the orientation plus, plus, minus, minus. And for the 4 cell, That's the famous pentagon. You attach a full cell using the pentagon. And this is minus, minus. And then everything else above is trivial. So that's give you this classifying space. And as my question, I don't know anybody has calculated homology or cohomology or this space. No, RP infinity. Yeah, there's nothing above. Just 5 cell attached, like a kind of drawing, the trivial thing, trivial disk. That they just homotopically attach, like nothing there. It's just contractible. There's a little bit of subtlety I'm hiding. If you really want to study a 3-groupoid, it's very complicated. It's an infinite groupoid. And the thing which is different is once you go to 3, 4, 5, 6, they're not completely trivial. Every 2 arrows are equivalent. So there's a little bit of a 4 dimension there. And for those who know higher category, the next one up here is called modification. And that's the up one.
But to understand B of a 3 category is still an ordinary space?
Ordinary space, yeah.
And that's the K-pi1?
It's not the K-pi1. That's what I'm saying. That's what I said. It will have 3 non-trivial homotopy groups. I will tell you.
Okay.
But its dimension is something like 5, right?
At this point, yeah, its dimension, 4 cells 5, yes. Homotopically. So that's basically my whole point of I try to sell to you that this, if my, first line says that, there's this potential conjecture came out of our work. If that's true, then we just need to calculate this space, the cohomology, the homotopy, and that should be the one for the moduli space. And then we should look for those parameters of Hamiltonian or Lagrangian to study their physics and everything. So now I want to basically say 2 things. One is a theorem. Again, the same ENO and the same paper, which is called homotopy theory and fusion category. This space B, Picard, the first group, which is the fundamental group, is the Picard group. The same thing as auto Brady tensor equivalent. So that's the first homotopy group. And the second one is abelian anyons. And the third one which is the one giving me most trouble, so it's a discrete, infinite, uncountable group, all the non-zero complex numbers. And you should notice this is so strange. This is independent of the category, just this. And that's the trouble. So the beginning of the whole story was Matt made a comment really impressed me, which is, I know this homotopy group, but I don't know how to make any physical story out of it. So we studied this one, and we realized it's responsible for the floquet code, the Hastings-Haah code. I'm always interested in what this guy means. And then Matt says something like, oh yeah, you can come up with 2-parameter Hamiltonian and get a fermion, which is the easy one of the toric code. And then I challenged him to do the boson. It was quite challenging. We wrote a 2-parameter family to do the map from pi2 to this space to a billion anyons. We have a map back and forth. It's not a mathematical theorem, but we have a map. And we also have a map going back and forth, which is a generalization of famous Kitaev's correspondence of the unrolling, what's it called? Anyway, so actually it's inside Matt's talk. So that's basically a generalization of Kitaya's work for B is WAC. And then this is something else. This I still don't quite idea. You can ask Po-shen. He says something about Berry phase. Okay, I want to make one comment. I believe this is responsible for the Berry phase in H-4. And I think that's what it is. Okay, so that's basically my definition. I think I have 10 minutes. So that's my definition of this space. And I really hope some student here can calculate this space, okay, thing I want to mention, the cohomology. So if you are a topologist, you don't have to be trained, just you went to enough talks, you would know that if you give me any group G, if you do BG, and then you calculate its cohomology, and that's something extremely interesting. And this is called universal characteristic classes. All the things, LPT, SPT, or something, just a pullback of cohomology from here. So the way you do it is that you take any space X, you take a continuous map here, and then you have this EG. You pull back this EG into a bundle, and that's a principal bundle. And the deep theorem is that's all. Every principal bundle comes from this construction. So that's why it's called class-infinite space. And once I mention this, obviously you can see all I want is to calculate the cohomology of this guy. And then ask the question what it tells us about physics, error correction, all those things. So in principle, if somebody can calculate by using this information, that will already tells us roughly what we should look for. There's one bit of information, actually not one bit, there's a little bit of information missing in here for those who study topology. We know the homotopy group, not enough for you to construct a space. This gives you the stages of the Postnikov tower. You also need the K invariant. I cannot calculate those ones by categorical thing. So therefore, what I want to do is, so I want to give you evidence why I believe the conjecture. First, in the paper of Dave and Matt, we construct the map back and forth. For the toric code, we construct this map back and forth at the physical level. I don't know how to do this one. And what I want to do now is, with the Perchin's work, I will tell you evidence that why this should match up with a cohomology like this. So I think I have a few minutes, probably enough for me to finish up. As I said, it's an advertisement. So this is the effective theory approach. So what I want to do is basically understand the cohomology of, B, Picard B. And I was learned from symmetry enriched TQFT, what I should do is take my three-dimensional space-time, map into B Picard. I really don't want to think about it. What I really want to think about is the module size space of Hamiltonian or Lagrangians. And I want to study the topological gauge theory for this higher gauge group. I don't know how to construct this space. I have a definition. So what we're going to do is, let's think about, this is for manifolds now. Let's think about finite dimensional manifolds inside this space. And I'll study TQFT enriched by this kind of thing. And I will just mention two examples. So, which in our paper is, I will try to impress you, try to write down a theory. So I will study two cases. the manifold is the two-sphere. And then I claim this two-sphere will trap anyons. In space-time. I will do a second mention it for M to be the full torus. And then I have H upper 2 of the full torus. This is pi 2, the abelian anyons in B. And in topology, actually, to define the cup product, you first do this. So that's the first step of the cup product. And then you use the multiplication of this, reduce to A. That's the standard cup product. But I don't want to do that. I want to do a different multiplication. I want to multiply this to U1. And this is an incredibly beautiful map, which is in every homotopy group, pi 2 goes to pi 3. And it's called a Y-hat bracket. And actually, this particular case is just a double braiding. So I will use this map, send this to pi 3, because this is A, and pi 3 is a C, and I can treat this as U1. And we can write down things to claim this is non-trivial. So therefore, it tells me in general, this space is not a direct product of three things. There are non-trivial Poisson, I think, of K invariant. So I think the last thing a few minutes, I want to tell you a little bit about this case, which is a homological version of the map we had, which is how to map pi 2 to abelian anyons. And so I will just write down what this is. And I'm pretty sure I can answer every question you have. So we have a two-sphere inside the whole moduli space. And I have a 2+1 space-time, a manifold. And I have a map. And the physical term is that, and now I want to think this as a background field of a field theory. And the way we want to do it is I will realize Zn toric code using 3 U1 gauge field and 2 scalar fields. And the Lagrangian so the Lagrangian depends on this two-sphere and depends on two integer modulo n. And there are 3 gauge fields, and there are 2 scalar. And this is, okay, I'll do my best. This is some constant, don't worry. And this is standard field theory. So if you study Chern-Simons theory, there's not something too surprising. I will write down the potential quickly later. So this is the coupling of the gauge field with, this is a continuous version how to implement discrete gauge theory. So to implement Zn gauge theory, you choose 2 continuous gauge fields, and then you condense those 2 scalar fields. That give you Zn. And then there's a coupling. And then this is just standard field theory. So the last thing I want to write down is the potential. And you can tell at this point, now the two spheres show up. So it has to be in the potential. And the potential is so that's the potential for this field theory. And then the claim is that when you condense this two scalar field, which you have to do to implement discrete gate theory, and then this U1 will Higgsized, and then you are left with those things. So the effective theory, when some mi squared equals some number, non-positive, it's become dA 2 pi, no, lambda star omega so this is called BF theory. And this is the coupling. So this term does is omega is the two form for the two sphere inside your moduli space. You pull back this two form into your space-time, and then this coupled to this abelian anion. So the claim is that this low energy effective theory, once you condense the scalar, and then this dA is become the pullback of the two form, and then this two sphere in X trap the abelian anion alpha with topological twist e to pi I. So that's what it is. And in terms of picture, and this is your two sphere. And imagine this is your anion there. High energy, you can see this much better. So high energy would tell you this is a WZW term, which is just a generalization of a Berry phase. And then this term tells you if you run a solid pump across this two parameter space, and you will get a charge, a skyrmion. And the charge is the anionical charge. So that's their story. I think I should stop here. So I think that's my advertisement.